let's try to come up with a reaction of when we have this molecule right here reacting with sodium methoxide in a methanol solution, or with methanol as the solvent. With methanol as the solvent. And just so we get a little practice of naming, let's see, this is 1, 2, 3, 4 carbons. So it has but as a prefix, no double bonds or triple bonds, so it is butane. And we have a chloro group here, so if we start numbering at the side closest to it, 1, 2. So it's 2 chloro. This is 2 chlorobutane. So let's think about what might happen here. So the first thing, let me just redraw the molecule right there. The first thing you need to realize is this sodium methoxide, it is a salt. It is, when it's not dissolved, it's made up of a positive sodium cation. Let me draw them right here. A positive sodium cation. A positive sodium cation and a negative methoxide anion. So let me draw the methoxide part right here. So a negative methoxide anion. And then it has, so normally we would have just 2 pairs, but now we have 3 pairs here. The oxygen has an extra electron. The oxygen has an extra electron. Actually, let me draw another electron as the extra electron. This will be useful for our mechanism. So it could be any of them. But the oxygen has an extra electron, it has a negative charge. In solid form, when they're not dissolved, they form an ionic bond and they form a crystal-like structure. It's a salt. But when you dissolve it in something, in a solution, in this case we have methanol as the solution, they will dissociate from each other. And what you have right here is this methoxide right here. This is a very, very, very strong base. So this right here is a strong base. And if you use the Lewis definition of a base, that means it really, really, really wants to give away this nucleus to something, this electron to something else. If you use the Bronsted-Lowry definition, this means that it really, really, really wants to take a proton off of something else. And in this situation, that is exactly what it will do. And I'll just give you one, I'll actually give you the most likely reaction to occur here, and we'll talk about other reactions and why this is the most likely reaction in future videos. So it wants to nab a proton. It is a strong base. It wants to give away this electron. So let's say that it gives away this electron. It gives away to this electron to this hydrogen right over here. Now, this hydrogen already had an electron. If it's getting an electron from the methoxide anion, the methoxide base, then it can give away its electron to the rest of the molecule. So now it can give away this electron to the rest of the molecule. Now, carbon won't need the electron. Carbon doesn't want to have a negative charge. Maybe simultaneously that electron goes to that carbon right over there. But once again, this carbon doesn't want it. It only has 4 bonds. But what we see is we had this chloro here. This is a highly electronegative, I guess you could call it a group right now. The chlorine is very electronegative. So the whole time, the chlorine was already tugging on this electron right here. So now all of a sudden, this is all happening simultaneously. When an electron becomes available to this carbon, then now this carbon doesn't need this electron anymore. The chlorine already wanted it. So now the chlorine can take the electron. And just like that, in exactly one step, let's think about what happened. If all of this whole chain reaction, and I shouldn't call it a chain reaction, this simultaneous reaction occurred, what are we left with? What are we left with? So let me redraw my 2-chlorobutane, but I'm going to have to change it now. So now the chlorine, this has disappeared. So let me clear it. That's disappeared. The chlorine has now left. It has now left. This chlorine is now up here. It is left. It had this electron right over there, which is right over there. And then the electron it was paired with, that it was forming a bond, is now also on the chlorine. So now it becomes a chloride anion. So now it is a chloride anion. If I want to draw the rest of, let me draw the rest of the valence electrons. 1, 2, 3, 4, 5, 6, and it had the seventh one right here. 1, 2, 3, 4, 5, 6, 7, 8 now. So it now has a negative charge. Now this electron up here, let me clear this part out as well. So let me clear that out as well. Now, this electron right here, this magenta electron, this is now given to this carbon. So let me draw it here. So that magenta electron is now given to that carbon. And if we look at the other end, the one that was paired with, it was bonded with, it still is bonded with it. So that green electron is now still on that carbon, and now they are bonded. And now they're forming a double bond. So now they are forming a double bond. This all of a sudden has become an alkene. And now the methoxide took the hydrogen. The methoxide took the hydrogen. So let me redraw the methoxide. So OCH3. The oxygen had 1, 2, 3, 4, 5. It had 6. Well, actually, it had 8 valence Actually, it had 7 valence electrons, one with the carbon, and then all of these 6 unpaired ones. Neutral oxygen has 6, but now it gave one of them away to a hydrogen. It gave that green electron over there to the hydrogen. It gave that green electron over there to this hydrogen. Let me do it. I'll make this hydrogen the same color. To this hydrogen right over here. So now this hydrogen is now bonded with it. This hydrogen is now bonded with it. So what are we left with? We have a chloride anion. We have a chloride anion. So this is chloride anion. We now have methanol. This was a strong base. Now it has become its conjugate acid. So now we have methanol, which is the same as the solvent, same as solution. So it kind of just, or actually same as the solvent. So it's now mixed in. And now we're left off with 1, 2, 3, 4. Still 4. We still have 4. We still have 4 carbons. But now it's an alkene. We have a double bond. So we could call this but2-ene, or sometimes called 2-butene. So let's think about what happened here. It all happened simultaneously. Both reactants were present. There was actually only one step, so this is the rate determining step. So if we were to try to name it, we'd probably have a 2 in it someplace. And something got eliminated. The chloride, or I guess you could call it the chloro group, got eliminated. It left. It was a leaving group in this situation. So this was eliminated. This was eliminated. And this type of reaction where something is eliminated and both of the reactants are participating in the rate determining step, and we only had one step here, so that was the rate determining step, is called an E2 reaction. E2, it is called an E2 reaction. And once again, E stands for elimination. Elimination. And the 2 stands for that both reactants involved in the rate determining step. We had 1 reactant and 2 reactants. They were both involved in the rate determining step. E2, just like SN2. I mean, it's obviously not the same reaction, but SN2 had substitution. When leaving group left, nucleophile came. It was a substitution using a nucleophile, so that's the S and the N. And then the 2 was we had both reactants. It was all happening simultaneously. I'll leave you there. We're going to go into more detail on the different types of E2 reactions, which ones are favored, and then we'll talk a little bit about E1. And you can maybe guess what that's going to be based on our experience with SN2 and SN1.